Today we're going to talk about resonance, and we're going to talk about standing waves. Now, resonance occurs when the frequency of a force you apply matches the natural vibrating frequency of an object. So objects have a natural frequency they vibrate at. When you apply a force at that frequency, they will begin to vibrate. You've all seen this with the swings. When you want to push someone higher on the swings, you push them once every cycle. You push them with a frequency that matches their natural frequency of vibration, and they swing higher. Now, another example of resonance occurred with the Tacoma Narrows Bridge in the 1940s. So I'm going to show you a little bit of a video clip here. Let me pull it up. So here we're going to see part of a video clip of the Tacoma Narrows Bridge. And the vibrational frequency of the bridge matched the natural vibrational frequency of the wind through that area. And so as the wind blew through the area, the bridge began to resonate. So you can see the bridge just twisted and turned and vibrated. They called this bridge Galloping Gertie. Now I'll provide you with the video link for this so you can listen to it with the original sound as well. It's kind of a nice example of a 1940s newsreel. You can see the bridge is about to collapse here. And it finally collapsed. So the Tacoma Narrows Bridge was a very powerful example of resonance. We also want to talk about standing waves. Now, standing waves are very important with musical instruments. In a standing wave, they're really an interference effect. Now, we looked at one interference effect with beats where we had waves of slightly different frequencies interfering. In order to get standing waves, you need to have two identical waves interfere. And that's what occurs in musical instruments. So when you listen to a guitar, you have a standing wave in a string. And the guitar string has transverse waves in it, which then produces the longitudinal sound waves in the air that we hear. So if we consider standing waves in strings, the string is fixed at both ends. That means there has to be a node at each end. Now, nodes and antinodes were terms that we defined with our wave properties. The node was a point of no motion or zero displacement. So the first harmonic or the first option for a standing wave that we have would have a node at each end and one antinode in the middle. And that's called the first harmonic. So you cannot get standing waves with just any frequency or wavelength. Depending on the length of the string and the conditions, you only can get specific waves to produce standing waves. The specific waves that make standing waves have a node at each end. So here we'll look at a diagram, and here we have a node at each end of this string. And we can see in the fundamental or the first harmonic that the length of the string is half a wavelength. So that's what sets up our fundamental or our first harmonic. And each higher harmonic is based after that. In the second harmonic, we have two half wavelengths. In the third harmonic, we have three half wavelengths, and so on. So let's take a look at a little video that's going to show us a standing wave in a string. And this is a video resource from your textbook. So here we're going to see a little video clip, and this video is actually from your textbook, so you can go back and watch it again if you'd like. He's going to set up some standing waves in this string. So he's got a string here, and he's got weights at the end to keep it under tension, and then he's going to produce some standing waves.
Right here. You can see that we have two
so it's going to be fixed at each end.
This rope way on the end. And those are keeping our rope in tension.
And when he plucks it, you can see that we get a node at each end, and we get the fundamental frequency.
Vibration, a wave crosses the rope and then reflects off the end and comes back. Well, if we repeat that over and over, what will happen is that we'll create.
So in a second here, he's going going to increase the frequency and set up some standing waves. So he's going to vary the speed of the thing producing the waves to create the different standing waves. So here we can see we have the fundamental, and as he increases that frequency, eventually we're going to get the second harmonic with a node right here in the middle. See that node right there, that place that's not moving. And then as he increases the speed some more, he's going to produce higher harmonics. And we'll be able to see the nodes and the antinodes produced. Okay, so here's a node. And from the side, you can see it a little better. Again, your nodes and your antinodes are here in the middle. And you can see sometimes it's not setting up a very good pattern. That's when he's not right at the correct frequency for that harmonic. So only certain frequencies will set up standing waves. And here we have a higher harmonic with multiple half wavelengths. So that shows us our different harmonics that go with the waves on the string. So the number of the harmonic is given by the number of half wavelengths that fit into the length of the string, and that's important to remember. We also know that the speed of the wave is equal to the frequency times the wavelength. So we're going to take and write that expression here, and we're going to write it for the fundamental frequency, or F1. So it would be V over the wavelength for the fundamental, but the wavelength for the fundamental is equal to twice the length of the string. So we can substitute that in for lambda. And that gives us the equation for the frequency of the fundamental wave. Now, what if we don't want the fundamental? What if we want the second harmonic, or the third harmonic, or the fourth harmonic? Well, it becomes very easy. All we do is multiply the frequency of the fundamental by the harmonic number. The harmonic number is given by n, so it's always going to be an integer. And then we multiply by the equation that we got for the frequency of the fundamental, and we get the equation for any harmonic for waves on a string. So string instruments aren't the only kind of instruments we have. We also have wind instruments. And in wind instruments, you have standing waves, but they're longitudinal waves, and they're in the column of air. So we have longitudinal waves in air that are producing standing waves in wind instruments. Now, wind instruments can get fairly complex. If you look at a wind instrument, there's multiple openings. You can open and close them. There's different lengths. So we're going to consider very simple situations of just straight pipes. So we're going to first look at a pipe open at both ends. Now, when the pipe is open at both ends, because it's open at both ends, the air particles are free to move. And if they're free to move, that means we need an antinode. Now, for the strings, we had nodes at each end. For the pipes open at both ends, we have antinodes at each end. But an interesting thing happens. Because antinodes are half a wavelength apart, the fundamental is still based on half wavelengths for pipes open at both ends, because it's from antinode to antinode. So if we take a look at a diagram of that, here we have an antinode and another antinode, but our fundamental, or our first harmonic, is still corresponding to the length equaling half the wavelength. So the equations for harmonics for strings and for pipes open at both ends turn out to be exactly the same, which is kind of nice. If instead we have pipes open at one end and closed at the other, at the open end you have to have an antinode, and at the closed end, though, you have to have a node. In this case, the distance between one antinode and the very next node is 1/4 of a wavelength. That means our first harmonic, or our fundamental, is corresponding to 1/4 of a wavelength in the length. And then our next one would be 3/4 of a wavelength. So instead of having a 2 on the bottom here, we have a 4 in our equation. And we also notice that if we look at our harmonic numbers, you're not going to get any even harmonics, because even harmonics would simplify to having a 2 down here instead of a 4, and we need everything to be based on quarter wavelengths. So for pipes open at one end and closed at the other, you have a different equation than you do for strings and pipes open at both ends, because your fundamental is based on quarter wavelengths instead of half wavelengths. So we can look at a diagram of that as well. So here we see a node at the closed end and an antinode at the open end. And that gives us a quarter wavelength equaling the length for our first harmonic. Now there's no way we can have a second harmonic here, because you would never be able to get a node at one end and an antinode at the other end fitting 2/2 lambda in the length. So we have to skip to the third harmonic with a node at one end, an antinode, another node, and then one more antinode. So you're only going to have odd harmonics when you have tubes closed at one end and open at the other. The harmonics are what give a musical instrument its tone or its timbre. So when you have a tuning fork, you get basically a perfect sine wave, and you're really only getting one frequency. When you play a musical instrument, you're going to get the predominant frequency, or the fundamental, but then you're also going to get different intensities of the higher harmonics. So this is what makes listening to a banjo sound different than listening to a guitar. Even if they're playing the same notes, the amount of the higher harmonics is different for each, and that's what gives it its timbre or its tone.